Solids exist in different shapes and sizes. The molecules within a solid body occupy fixed positions and their relative distance of separation remains constant. The molecules are in equilibrium with each other and experience no net force. The graph displays the intermolecular force between two molecules as the distance of separation between them changes. When molecules are at the equilibrium distance of separation, there is no net force between them. If they come closer than this, they experience mutually repulsive forces. The force becomes mutually attractive when the distance of separation is more than the equilibrium value. What happens when a body is subjected to an external force? The body accelerates in the direction of the net force according to Newton's second law of motion. If a body has a set of two equal and opposite forces acting on it, the net force is zero. In such a case, even though the body does not experience any net force or acceleration, the applied forces deform the body by changing either the shape or size of the object or both. When a body is deformed, the distances of separation between its particles changes from their equilibrium values. This change in intermolecular distance generates intermolecular forces. The distance of separation having increased from the equilibrium value, the molecules experience mutually attractive forces. When the deforming forces are removed, these intermolecular forces try to restore the body to its original shape and size. This property of a body, by virtue of which it regains or tries to regain its original shape and size when deforming forces are removed, is called elasticity. The material is called an elastic material. There are some materials that offer little or no tendency to regain their original shape and size even when deforming forces are removed. Such materials are called plastic, and this property is called plasticity. Putty and mud are almost perfectly plastic. A body can be deformed in one or more of three possible ways, namely longitudinal deformation, volume or bulk deformation, and deformation in shape. If two equal and opposite forces are applied perpendicularly to opposite faces of a body, the length of the body along the line of action of the forces changes. The length will increase for outward forces and decrease for inward or compressive forces. If forces are uniformly applied in all directions on a body, the dimensions of the body undergo an overall change, leading to an increase or decrease in the volume of the body without altering its shape. If two equal and opposite forces act parallel to two opposite faces of a body in a tangential direction to the surfaces as shown, the shape of the body gets distorted. Based on the way in which deforming forces act on a body, the length, volume, or shape of a body changes. When a body is deformed, the intermolecular distance of separation changes from its equilibrium value. This causes intermolecular forces to be generated, which try to restore the body to its original state once the deforming external forces are removed. The sum total of intermolecular restoring forces per unit area is called stress. Stress is measured as the deforming force applied per unit area. If F is the force applied on the surface of a body with an area A. Then, stress is equal to force F by area A. Stress has units of 1 Newton per meter square, which is also called 1 Pascal. Its dimensional formula is ml to power minus 1 t to power minus 2. The fractional deformation produced in the body by the external deforming forces is called strain. It is calculated as the ratio of the change in the body's dimension to the original value of the same dimension. For example, if the original length of a rubber band is L and the increase in its length is delta L, then the strain is equal to the ratio delta L to L. As strain is the ratio of two similar quantities, it has no units. Thus, strain is a dimensionless quantity. A body can be deformed in one or more of three possible ways, namely longitudinal deformation, volume or bulk deformation, and deformation in shape. Based on the manner in which deforming external forces are applied and deform a body, we define three different types of stress and strain. When deforming forces are a pair of equal and opposite outward forces, applied normal to a pair of opposite end faces of a rod, the length of the rod increases, and the stress generated is called tensile stress. When the deforming forces are a pair of equal and opposite inward forces, applied normal to a pair of opposite end faces of a rod, the length of the rod decreases, and the stress generated is called compressive stress. Inward or outward deforming forces applied along the length of a body causes a change in its length. The change in length causes tensile stress or compressive stress, and these are collectively called longitudinal stress. Longitudinal stress is measured as the ratio of the applied force F to the area of the face A. If the length of the rod L changes by delta L, the fractional deformation, called the longitudinal strain, is equal to the ratio of delta L to L. When deforming forces are applied perpendicularly to a body's surface at every point, the volume of a body changes, and the stress generated is called bulk stress or volume stress. Forces acting perpendicularly inward at each point on the surface of a body are equivalent to a uniform increase in external pressure. Therefore, bulk stress is defined as a change in pressure delta P. If the volume of a body V changes by delta V, then the fractional deformation, also called the bulk strain or volume strain, is equal to the ratio of delta V to V. If two equal and opposite forces act parallel to two opposite faces of a body, the shape of the body is distorted. When the deforming forces are a pair of equal and opposite forces applied tangentially to a pair of opposite end faces of a body, the shape of the body is distorted, and the stress generated is called tangential stress or shear stress. Shear stress is measured as the applied tangential force F divided by the area of the face A. When a force is applied to the top surface of the body tangential to it, the top surface is displaced laterally with respect to the bottom surface by length dx. Simultaneously, the vertical face of a body normal to the direction of the force applied is tilted through an angle gamma from the vertical. If the vertical height between the two horizontal surfaces is h, then using the geometry of the right triangle, we get the trigonometric ratio tan gamma is equal to dx by h. For small angles, the value of tan gamma is nearly equal to gamma, and hence, for practical purposes, we consider gamma equal to dx by h. This gamma is the shear strain of the material of the body and is expressed in radian. The dimension perpendicular to the faces under the action of deforming forces rotates through a small angle gamma. The shear strain is equal to the value of gamma expressed in radians. Robert Hooke found that for most materials, for small values of strain, the stress is directly proportional to the strain. Thus, we have stress is equal to K into strain, where K is the constant of proportionality called elastic modulus of the material. If on increasing the stress, the strain is increased beyond a certain value, the proportionality between stress and strain is lost. There are some materials that do not obey Hooke's law. For example, for materials such as polymers like rubber, human muscles, and blood vessels, stress is not proportional to the strain. The relationship between stress and strain of a deformed body depends on the material of the body. The actual stress-strain graph for a body depends on many factors, such as its material, its temperature, and whether it has previously undergone any deformation. The way in which strain changes with stress for any material can be studied experimentally. The corresponding values of stress and strain can be then plotted on a graph. This graph is called the stress-strain curve. In a typical experiment to study the relationship between tensile stress and strain, the material in the shape of a rod or wire is held fixed at one end. The other end of the rod is subjected to a load, which is increased in stages. The elongation of the rod is measured at each stage. A machine used for stress testing is shown on the screen. The two ends of the rod are held between the top and bottom grips. One end is fixed and the other end is pulled to apply a precise load. The stress is calculated by dividing the load F by the original area of cross-section A of the rod. The strain is calculated by dividing the elongation delta L by the original length L of the rod. A typical stress-strain graph is shown. In the initial part of the graph, for low values of strain, the stress-strain curve is a straight line. In this straight line region of the graph from O to A, stress is directly proportional to the strain and Hooke's law is obeyed. Point A is called the proportional limit. As the strain increases further, the graph no longer remains a straight line. However, in the region of the graph between points O and B, If the load is removed at any point, the body completely regains its original length. Point B on the graph is called the elastic limit. The stress corresponding to elastic limit is the maximum stress the substance can withstand and without any residual strain when the load is removed. Beyond the elastic limit B, the strain increases at a faster rate than stress, shown on the graph between points B and D. Even if the load is removed, the substance does not completely regain its original size. The deformation is now called plastic deformation. The value of the stress at point B is called yield strength because this is the minimum stress required to induce plastic deformation. Yield stress is denoted by the symbol SY. So, point B is also called the yield point. The amount of residual strain that remains on removing the load can be determined from the stress-strain curve. For example, if the load is reduced to 0 from point C, the residual strain can be found by drawing a line parallel to OA at C. The point where this line intersects the strain axis gives the residual strain or permanent set. The stress now increases with strain, but less rapidly. The material experiences maximum stress at point D. The value of stress at this point is called tensile stress or breaking stress and is denoted by the symbol SU. It is also referred to as ultimate tensile strength. The stress is not uniform throughout the material. At a point in the material where there is a defect or weakness, all further plastic deformation is concentrated in this region, and the material begins to neck or thin locally. Because the area of cross-section now decreases very rapidly at the neck, the effective load at this point decreases, and so stress reduces till the material actually breaks or fractures at this point. The break point or fracture point is represented by point E on the graph. The stress-strain curve for different materials is different. For example, the stress-strain curve for mild steel and cast iron look different. The curve for concrete and cast iron shows no plastic deformation. This means that they are brittle and will break suddenly at the point of maximum stress. Mild steel experiences large strains for very little change in stress in the plastic region. Such materials have high ductility. So we can say that materials that strain by large amounts before fracturing are ductile, whereas those that rupture at low values of strain are brittle. Accordingly, the study of stress-strain curves for different materials can help scientists identify appropriate material to be used in the design of engineering structures. Consider a solid rod suspended from a rigid support and subjected to tensile force as shown. The stress-strain curve for most materials is a straight line for low values of strain. Hooke's law is obeyed along the straight OA on the stress-strain curve. Accordingly, stress is proportional to strain here, and the slope of the straight line on the stress-strain curve is called modulus of elasticity. More precisely, it is the ratio of stress to strain of an elastic body within its elastic limit. The slope of the straight line, OA, On the longitudinal stress, longitudinal strain curve is called Young's modulus in honor of the British scientist Thomas Young. Young's modulus is calculated as the ratio of longitudinal stress to longitudinal strain in OA and is denoted by the symbol Y. Longitudinal stress is measured as the ratio of the applied force F to the area A of the face to which force is applied. If the length of the rod L changes by delta L, the longitudinal strain is equal to the ratio of delta L to L. Young's modulus is therefore equal to F by A divided by delta L by L. Young's modulus has the same units as stress because strain does not have any units. Y is measured in newtons per meter square or pascals. Different materials exhibit different values of Young's modulus. The value of Young's modulus for some materials is shown on the screen. Metals generally have large values of Young's modulus compared to other materials. It is a common misconception that rubber is more elastic than a metal, such as steel. This is because you see a rubber band stretching to more than double its length very easily. But steel does not display similar extension. In scientific terms, the higher the Young's modulus of the material, the more elastic it is. This is because a higher Young's modulus means a larger force is required to produce the same amount of deformation in bodies of the same dimensions. The expression for Young's modulus can be rearranged to solve for F, the applied force. If bodies of different materials have the same area of cross-section A and the same original length L, then the material with a higher Young's modulus Y will need a larger force F to be applied to produce the same change in length, delta L. All load-bearing equipment is made or supported by materials such as steel because they are better able to withstand deforming forces. We will now solve a numerical problem. A load of 40 newtons stretches a wire of radius 1 millimeter and length 2 meters by 0.1 millimeter. Calculate Young's modulus of the material that the wire is made of. The values given in the problem are force F, length L, extension delta L and the radius R of the wire. Since wires have a cylindrical shape, the end face will be circular and the area of cross-section of the wire will be pi times R squared. Now, we substitute all the values in the expression for Y and calculate it. Y is 2.5 times 10 to the power 11 newtons per meter square. A 1.5 meter long copper wire is joined at one end to a 2 meter long steel wire of same area of cross section. The combined wire is stretched by a force of 200 newtons. What is the ratio of extension of the copper and steel wires? Young's modulus for copper and steel are 1.1 times 10 to the power 11 and 2.0 times 10 to the power 11 newtons per meter square. The values given in the problem are the original lengths of the two wires, load, and Young modulus for each material. We write the expression for Y for the copper and steel wires. We divide equation 1 by equation 2 and cancel out the equal values of areas of cross-section and the force F. We rearrange the equation to get the ratio of delta L steel to delta L copper. Now, substitute values into the right side of the expression. We simplify to get the ratio of extension of the copper wire to steel wire as 11:15. Young's modulus for a material can be determined experimentally. The apparatus used to do this consists of two wires of the same material of about the same length suspended from a rigid support. At the lower end, the two wires support rectangular frames. The frames themselves support a spirit level between them. From the lower end of one of the frames hangs a fixed load, which keeps the wire taut. This wire is called the reference wire. From the lower end of the other frame hangs a pan that can be used to apply different loads to the wire. This wire is called the experimental wire. The original length of the experimental wire is measured using a meter rule. The radius of the experimental wire is measured at different places using a screw gauge. The area of cross-section of the wire is calculated as the product of pi and square of the average radius of the wire. The frame on the experimental wire has a short main scale, calibrated in millimeters, against which a micrometer screw moves. One end of the spirit level rests on the tip of the micrometer screw. The micrometer screw is moved to make the spirit level horizontal, and the micrometer reading is noted. As a load is added to the pan on the experimental wire, the wire gets extended and the spirit level no longer remains horizontal. The micrometer screw is moved up to make the spirit level horizontal again, and the new reading is noted. The extension of the experimental wire is equal to the distance covered by the micrometer as it moves up. The load is increased by an equal amount, and each time the micrometer is moved up to return to a horizontal position and the reading noted. The difference between the reading with the load and without the load is used to calculate the extension caused by that load. A graph between extension and load is plotted. It is a straight line for low values of strain. Young's modulus is calculated using the expression for Y. The ratio of force F to extension delta L is calculated from the extension load graph, and the values of L and A are substituted. In this experimental method, tensile forces were used to determine Young's modulus. Similar results are obtained even if the load causes compressive stress by using a suitable experimental setup. We learned that Young's modulus can be experimentally determined by applying different tensile or compressive loads and measuring the change in length in each case. Consider a cubical body as shown. When a pair of equal and opposite forces is applied tangentially to opposite end faces of the body, the shape of the body is distorted and the stress generated is called tangential stress or shear stress. Shear stress is measured as the ratio of applied tangential force F to the area of the face A. When a tangential force is applied to the top surface of the body, the top surface is displaced laterally with respect to the bottom surface by a small length dx, and the edge perpendicular to these two faces rotates through a small angle gamma. Shear strain is defined as the ratio of the lateral displacement of the top layer of the solid with respect to its bottom layer, which is the ratio dx to h. This is equal to the tangent of the angle gamma, where gamma is expressed in radians. If the value of gamma is very small, tan of gamma can be approximated to gamma, and hence the value of gamma is calculated by taking the ratio of dx to h. The ratio of shear stress to shear strain for a material is the shear modulus or the modulus of rigidity and is denoted by the symbol G. Shear modulus has units of newtons per meter square or Pascal. The values of shear modulus for a few materials are shown. Most materials have shear modulus values lower than their Young's modulus, and typically about 1/3 of their Young's modulus value. We will now solve a numerical problem. A cubical block of steel of edge 10 cm is held fixed at the bottom face and a tangential force of 10 to the power 5 newtons is applied to the top face. Calculate the shear stress and shear strain. The modulus of rigidity of steel is 84 times 10 to the power 9 newtons per meter square. The values given in the problem are the tangential force, the edge of the cube, and the modulus of rigidity. We calculate the area A of the face to which the tangential force is applied. Each face of the cube is a square, so the area would be equal to the length of the edge squared. We express the length of the edge in the SI unit, meters, before calculating A, and A is 10 to the power minus 2 meters squared. Shear stress is the ratio of the tangential force F to area A. Substituting the values of F and A, we get shear stress to be 10 to the power 7 newtons per meter square. The modulus of rigidity is the ratio of shear stress to shear strain. Arranging the relation to solve for shear strain and substituting the value of G and shear stress calculated earlier, we get shear strain as 1.19 times 10 to the power minus 4. Remember, strain has no units. We will now learn about bulk modulus. When deforming forces are applied perpendicular to a body's surface at each point, the volume of a body decreases and the stress generated is called bulk stress or volume stress. Forces acting perpendicularly inward at each point on the surface of a body are equivalent to a uniform increase in external pressure. Therefore, bulk stress is defined as a change in pressure delta P, which is also equal to the ratio of force F to area A. If the volume of a body V changes by delta V, then the bulk strain or volume strain is equal to the ratio of delta V to V. The ratio of bulk stress to bulk strain is called bulk modulus and is denoted by the symbol B. Bulk modulus is equal to the ratio of delta P to delta V by V. An increase in pressure causes a decrease in volume, which means that a positive value of delta P causes a negative value of delta V. Therefore, the expression has a negative sign to give a positive result for B. Bulk modulus is measured in units of newtons per meter square or pascals. The reciprocal of bulk modulus is called compressibility and is denoted by K. The values of bulk modulus for a few materials are shown. Data shows that solids have the highest values of bulk modulus, followed by liquids and then gases. Gases have an extremely small bulk modulus. As compressibility is the reciprocal of bulk modulus, this means that gases have very large compressibility compared to liquids, and liquids have higher compressibility than solids. The compressibility and bulk modulus of gases depend on the pressure and temperature of the gas. The reason for the huge difference between compressibility of gases, liquids, and solids lies in the intermolecular forces of interaction in the three states of matter. The molecules of a gas are so far apart that there is a negligible interaction force between them. Liquids have a strong intermolecular force of interaction, whereas solids have the strongest interaction between their molecules. We will solve a numerical problem. A cubical block of steel has an edge of 10 cm when subjected to a pressure of 10 to the power 5 Pascal. What is the change in its volume when the pressure on it increases to 26 times 10 to the power 5 Pascal? The bulk modulus of steel is 160 times 10 to the power 9 Pascal. The values given in the problem are the length of the edge of the cube, the original and new pressures, and the bulk modulus of steel. The original volume of the cube is cube of the edge. Expressed in meters, the original volume is 10 to the power minus 3 meters cubed. The bulk stress delta P is equal to the change in pressure, and substituting the original and new pressures, delta P is 25 times 10 to the power 5 Pascal. Bulk modulus is the ratio of bulk stress to bulk strain. We rearrange this expression to solve for delta V, the change in volume. Substituting the values of delta P, V and B, we get the change in volume. Delta V as minus 1.56 times 10 to the power minus 8 meters cubed. The negative sign in the answer means the final volume is smaller than the original volume. Man has made structures such as skyscrapers and overbridges to make life convenient. Such constructions must be designed for safety. Otherwise, there could be disastrous consequences. The design of safe and appropriate structures involves choosing the appropriate material in appropriate shapes and size. Let's take the example of a crane used to lift heavy loads. The highest value of stress the crane's rope can be subjected to must be lower than the breaking stress value of its material. Consider a crane designed to lift loads of up to 1 ton. With a rope made of steel, of breaking stress 400 times 10 to the power 6 newtons per meter square. The cross-sectional area of the rope can be calculated by equating the breaking stress SU to the ratio of maximum load and the area of cross-section A. The cross-sectional area of the required rope is calculated for the maximum load of 1 ton. That is 1000 kilos. By substituting the maximum load as mass times acceleration due to gravity and the breaking stress. The required area is 2.45 times 10 to the power minus 5 meters square. As the cross-section of the rope is circular, which is equal to pi r square, substituting and simplifying for the radius, we get the radius of the rope as 2.79 millimeters. In practice, a large margin of safety is provided and thus a thicker rope, say of about 8 millimeters, is recommended. It is also found that a collection of thinner wire strands, when compacted together, make the rope stronger than a solid rope of the same cross-section. That is why crane ropes are made of several strands instead of one. Structures such as bridges and tall buildings that have to support static or dynamic loads are generally constructed using pillars and beams to support them. The beams used in buildings and bridges have to be carefully designed so that they do not bend excessively and break under the stress of the load on them. Let us consider a beam resting at both ends, subjected to a load W at its midpoint. The beam has a length L, width B, and thickness A. When a load is exerted at its midpoint, it bends as shown. In the process, the upper surface is compressed, whereas the lower surface is extended. The beam will sag or deflect due to the load. The deflection of the beam at the midpoint is its vertical deflection compared to its unstretched position. The greater the width B of the beam, the greater the maximum load of the beam can support. The deflection delta at the midpoint can be determined experimentally as well as theoretically calculated. As the calculation involves high-level mathematics, we avoid the derivation of the expression in our context. It is equal to the load W times the length L cubed divided by 4 times the product of the thickness A, width B cubed, and Y, Young's modulus of the material of the beam. It must be kept in mind that the beam bends less for a given load if the width B is greater and the length is smaller. This is due to the fact that the deflection of the beam due to the load is inversely proportional to the cube of the width and directly proportional to the cube of the length of the beam. Also, as the deflection of the beam is inversely proportional to just the single power of the thickness of the beam compared to the cube of width, the thickness of the beam does not have as great an effect on the maximum load that can be supported as the width. But on increasing the width B, unless the load is placed at the right place, there is every chance that the beam will bend as shown. Such bending is called buckling. Thus, the beam can buckle under asymmetric loading, which is the case in bridges that carry differently distributed traffic at different times. To avoid this, the cross-section of the beam is chosen to be an I-shaped, as shown. This shape provides a large load-bearing surface and enough depth to prevent bending. It also reduces the weight of the beam without compromising on its strength to bear loads. The pillars used in buildings and bridges are also modified to be able to support greater loads by making the ends distributed. The elastic properties of rocks can help calculate the maximum height of mountains on the earth. At the bottom of a stable mountain of height h, the stress must be less than or equal to the elastic limit of the rocks, even though there is no uniform distribution of the weight of the mountain on the rocks at the bottom. The stress due to the weight of the mountain at its base will be equal to h rho g, where rho is the density of the mountain rock and g is acceleration due to gravity. The stress due to the mountain's weight can be equated with the yield stress, the stress at the elastic limit. The value of yield stress for rocks is typically in the range of 3 times 10 to the power 8 Pascal. taking an average density of rocks as about 3000 kg per meter cubed, and solving for h, we get h as approximately 10 kilometers.